Thanks to Squarespace for sponsoring today's video. You may have wondered, with the vast distances between objects in space, and with the lack of a tape measure that big, how can scientists be sure they know the distances between us and other celestial bodies? Well, there are a few methods available depending on how far away the object is, each with a varying degree of accuracy. The first method is the most accurate, and in fact gives us very precise measurements. This is the parallax method. For those of you that don't know what the parallax effect is, it is where nearby objects appear to move more compared to objects far away as you travel parallel to them. For instance, when you look out of a side window in a car, everything close by whizzes by, but objects in the background stay reasonably still. How does this equate to measuring the distance between stars? Well, Earth orbits the Sun, taking 6 months to reach from one side to the other. Scientists can look at a star and record its position compared to distant stars beyond it. In 6 months' time, scientists can again record where the star is. Because we know the diameter of Earth's orbit is roughly 300 million kilometers, using simple trigonometry, we can work out the distance to the star. Is the star close to us? Then the differences in its apparent location will be much bigger. Is it further away? The star's position will only change very slightly because the angle is much smaller. This method works up until about a distance of 400 light years, as beyond that the change in its apparent motion can't be measured anymore. Earth's orbit would have to be a lot bigger before you could use this method for farther distances, which is unfortunate because most things in space are further than 400 light years away from us. But thankfully, there are very clever scientists out there that have come up with another method to judge distances without having to use trigonometry. Although it should be mentioned that this method is slightly less accurate. It's just simply the best we've got. It seems that stars tend to follow a pattern, which can be seen on this chart. Main sequence stars, which make up the majority of stars in the universe, can all be found somewhere along this band. Their temperature corresponds to their color, and most importantly, their brightness. Using stars that have a confirmed distance thanks to the parallax method, we can see how much a star dims due to the distance between it and us, and extrapolate that far beyond 400 light years. So, say we see a very blue star that we want to know the distance to. Once we know the star's precise color, we can tell how bright it would be if it were right next to us. We can then measure the star to see how bright it is from our perspective. Combining this with our extrapolated data, we can predict how far away the star really is. Obviously though, there is some margin of error in our predictions. This band is quite thick after all, not a precise thin line. So these two methods work for stars in our own galaxy, where they are still close enough to be resolved individually. But what about other galaxies? How do we measure the distances to them? Well, we would have struggled were it not for the universe being kind to us by gifting us Cepheid variables. A Cepheid variable is a very special type of star that changes in brightness periodically depending on how bright it is. And some of these stars are very bright indeed, so much so that the changes in brightness can be detected by us all the way in a different galaxy. Timing the pulses in a Cepheid variable, we can know exactly how bright the Cepheid variable should be and how dim it is to us, allowing us to use the extrapolated data again to work out the distance to it and to the galaxy it resides in. Beyond that, it gets much more complicated and less accurate. With galaxies billions of light years away, you have to start taking into account the expansion of the universe and redshift. And the distances make seeing the galaxies at all very difficult, as they require long exposure photos, which will blur the variations in light produced from Cepheid variables, assuming they are bright enough to be seen at all. However, the universe has given us one more measuring stick to work with, type 1a supernova. These are a very specific type of supernova, where in a binary star system, a dense white dwarf starts to cannibalize a larger red dwarf. Once the white dwarf hits a critical mass, the star becomes unstable and undergoes a runaway nuclear fusion reaction, producing an extremely bright event that can rival an entire galaxy in brightness. Because these supernovae always happen to a white dwarf that hits a very narrow range of mass, the rise and fall of their brightness is very predictable. And given they are very bright events, they have been used to measure distances of up to 13.2 billion light years. However, there aren't always these type of supernova going off, which means if scientists want to use this method, then they need to be very patient. There are a few other methods out there too, but this covers the main ones. To me, these are incredibly clever methods to measure distances, and credit to the scientists who came up with them in the first place. The only sad thing about realizing how far away everything is knowing how hard it will be to cover those distances should we ever want to explore beyond our own solar system. Here's hoping for more bright minds to come to the rescue in a few generations' time. Thanks again to Squarespace for sponsoring this video. Squarespace gives people a powerful and beautiful online platform from which to create your own website. I've been having a go with their platform, and I like the fact that you can integrate videos and audio seamlessly. They also have a mailing list and email campaign feature to get your message across to your subscribers that matches the voice and style of your website. So if you are looking to build a website, give it a go. If you use the link squarespace.com/Astrum, you can try it out for free and get 10% off your first purchase. Thanks for watching. If you liked this video, subscribe and check out the other Astrum Answers videos in this playlist. Want to help pick the next question? Become a patron or member and join in the polls. Links are all in the description. All the best and see you next time.